welcome to solving the quantum harmonic oscillator using the analytic method, the easy way, or more made easy. So I have put a lot more work into this video than I have any other video in the past, because I know that this method is very important, and it's also usually the one that is not only hardest to understand as a student, but it's also kind of overlooked by teachers. I mean, teachers usually just go through it, and I looked at a lot of videos online and a lot of books, and somehow people just don't teach everything. I mean, they just skip steps and say, oh, you can show that this and you can prove this, but they don't really do it. So I took a lot of time to make sure that I can prove every single thing, at least to the best of my abilities, so that you can understand it better, because at least I would have really appreciated if it had been that way when I began doing it. So let us get right into it. So let us solve the quantum harmonic oscillator using this analytic method. So first, let's begin by writing out the equation that we want to solve. So as before, this is just going to be the Schrödinger equation for the quantum harmonic oscillator. So now, how do we solve this? So what we usually want to do, now seeing this just as a normal differential equation, now what we want to do here is we would like to get to some form of d squared psi dx squared. This is equal to something proportional to psi. And then maybe apply a power series solution or see if it looks in any way that is suggestive. But we would like to get to something like that. So that is our first goal. Now, many textbooks now go ahead and say, oh, just introduce this change of variable. But I think that that is not a good way to teach this, because the way to go is just show people how it would be done. So let's do that. So first, let's just go ahead and factor out h bar squared divided by 2m, right? This term right here, so that we leave this minus d squared psi dx squared, we leave it isolated, okay? So now from this term, we have to factor out this h bar divided by 2m. So it's going to be m omega x divided by h bar squared times psi. This is equal to e psi. So now we can multiply, or basically divide by this term. Let me do it in the same line. So this right here, we go to the right side as 2m e divided by h bar squared psi. Okay, so now let us isolate this right here by subtracting this. Okay, so let's put it right there. So this is going to be minus this is going to be equal to 2m e divided by h bar squared times psi minus m omega x divided by h and all of this squared psi. Now we can just multiply by minus 1 so that we lose that minus right there. So it's going to be minus here, and this is going to be a plus. Okay, so far so good. Now comes the tricky part, because now we have to introduce, or we don't really have to, but it's really going to make it easier if we introduce a new variable. So we got that annoying m omega x divided by h bar. So we have to think of some sort of variable that we can introduce to make the notation somewhat cleaner. So the first thing that I would think of, and in fact that's what I tried the first time I saw this, is okay, I'm just going to introduce psi. I'm going to keep the same name that they use in Griffiths. And I say, okay, what could I use? My first intuition would be to just say this is m omega x divided by h bar. Okay, I don't know, but I do, but doing this for the first time, you don't really know if this is going to work, but this is the way you solve these equations. You just say, okay, let us try this. And if it doesn't work, then we'll just tune it and try again. So this is our first attempt. So if this is psi, then we're going to have that dx, which is down here, is going to be, we take the differential of this, and then we have to isolate x. So we're going to get that it is h bar divided by m omega d psi. Okay, so let me do this in the next page, actually, because I don't want this to be messy. I really want to make sure that you guys understand this well. And if you find this helpful, I mean, it really means a lot if you just let me know in the comments so that I can continue making videos. Okay, so now we want to put this into this equation here. So we're going to get d squared psi dx squared. Well, and this dx is actually just going to be the psi squared. and we have to multiply by this, right? It's going to be this divided by h m omega squared, but because it is dividing by this, we can just flip it, right? And just write it here as it's going to be m omega divided by h bar squared. So it's going to be this is equal to minus 2 me divided by h bar squared psi plus psi squared psi. So this right here looks very good. We really like that. That's kind of what we would like to achieve. But now we have the small problem that in order to leave this alone, we have to divide by this. So this psi right here, what we're going to be left with is going to be d squared psi d psi squared. This is equal to, let's see, when we divide by this, we're going to be left with minus 2e divided by m omega squared psi plus psi squared h bar squared m omega squared psi. So this didn't really work the way we wanted to, and that's normal. I mean, I purposely wanted to do this step that was actually wrong because I wanted to show you that it's normal to just do trial and error in this sort of differential equation, because differential equations are like this. In the books, they just tell you, oh, just go ahead and use this change of variable, but you don't always know what the change of variable is going to be. So what we now have to do is see, okay, what's the problem here? We kind of overshot our guess. We have these high powers of h, m, and omega. If we had only taken this square root, then things would have been different. So let's try now taking just the square root of m omega h bar, not of the x. The x is outside. So our dx is just going to be the square root of this. Okay, so now I'm just going to erase all of this, and we're going to try again, but with this new change of variable. Okay. So in this case, we get d squared psi, and this dx is now d psi squared. And this time we are going to get, let's see, it's going to be m omega divided by h bar, and it's not going to be squared this time because the squared took out this square root. And this is going to be minus 2me divided by h bar squared psi. And then we have this term right here, which is going to be plus m omega divided by h bar psi squared psi. Okay, so this is really important. Now it's a lot better. By the way, just to make sure, here one of these m omega h bar went into the variable and the other one stayed outside, right? So now we have to divide by this quantity, right? So this quantity will cancel out this, and here we are going to get the following. So it's going to be d squared psi d psi squared, that's a d. This is going to be equal to, let's see, minus, the m's will cancel out, so we get minus 2e divided by h bar omega psi plus psi squared psi. And this is a lot better because we can now factor this as psi squared minus 2e divided by h bar omega psi. And this is of the form that we wanted. And we can now even say, okay, let us call this right here k, you know, because it's just a constant, so whatever, just call it k. So I'm going to erase this and just use this new notation. So this is going to be psi squared minus k times psi. So now we rewrote the Schrödinger equation as this. So this is what we now have to solve, and as you can see, it looks a lot better than what we started with. So this whole first step was just to make our equation look better so that it is cleaner. Okay, so that is what we were doing this entire time. Now we have to begin solving it, and well, this is not particularly easy. This is not an easy equation to solve at all. So if you want to try and solve it, go ahead, but you're going to notice it's not something we can just go ahead and do. So what we can do is use some mathematical techniques in order to solve this equation. So one method to do that is to use what's called an asymptotical solution, right? So what we're going to say is, okay, let's first look how this function psi behaves when we go to plus infinity and minus infinity, right? Let's see what happens when we go very far away from the origin. Basically, when our psi is very, very large, right? That's what this psi goes to infinity means. It means psi is going to be very large. When that happens in this equation, this term psi squared will dominate over this square k, which is just a constant, but this is going to be growing to infinity and at a rate of psi squared, so it's even faster. So when we are close or when we are dealing with very, very large values of psi, our equation will look very much like this equation. So if we solve this equation, then we will know what something that has to be in our function. It's not going to be just our solution, because this is not the equation that we were solving, but this is going to give us a lot of valuable information. So that is why we do this in books that usually don't really explain the procedure, but it's basically because of that. We really can't go ahead and just solve that differential equation. It's way too difficult, especially for undergraduate level. So we have to go to this asymptotic equation. Now, solving this one is sadly not too much easier. So there is something that you can do here. So, and usually in books, again, they just say, okay, this is the solution, check it. But let's say that we want to actually solve it. So using power series method, for example, you could solve it, but it is actually quite difficult. So I gave it a lot of thought as to how we could best find the solution. And my idea was the following. I'm going to need some more space, so I'll go to the next slide. So let us take a look at the following. So when we derive this equation, this function twice, we get this variable squared times that function, right? So it is not crazy to think that if we derive it only one time, so d psi, it might be that that is just something like psi times psi. Now, I don't know if this is true. As I said, there is a lot of guesswork involved in solving differential equations. And that's why I don't like that in book they just give you the answer and say check it, because it is normal to just try different techniques and see what works. In fact, I had to try several techniques in order for this to work. This wasn't my first try. So let's take a look at this, right? So if we do separation of variables here, we get that d psi divided by psi is going to be psi d psi. Once again, I really apologize if there's any Greek people here watching me butcher the letter psi. I'm really sorry. I really don't know how to draw it. So this is going to be the natural logarithm when we integrate of psi equal to psi squared divided by 2. So if we now exponentiate this, we get that psi, well, plus c, obviously. This is going to be some constant times e to the psi squared divided by 2. And obviously, we could have done the same procedure with some sort of a minus sign there. So another valid solution would be b to the e minus psi squared divided by 2 with the exact same reasoning. So this here is just guesswork. I have no idea at this point if this is going to work. I'm literally just hoping for this to work. Like, that is the way it is, okay? I'm gonna be honest with you. At this point, but obviously I do know that it's gonna work. I've done this before, but the first time you do this, you are just hoping, okay? It's just knowledge of what we have seen before and how you think this is going to behave. Okay, so now we have to actually see if this works. Okay, so now we have to see if this is a solution for the differential equation d psi squared equal to psi squared minus k psi. In the limit, remember, this is only supposed to be valid when this solution, when psi is very, very large, right? So let us see if that works. So if we differentiate this once, well, I said once. If we differentiate it once, let us, I'll do both at the same time, whatever. It's going to be a times psi e to the psi squared divided by 2 minus b psi e to the minus psi squared divided by 2. And differentiating a second time, we get a e to the psi squared divided by 2 plus a psi squared e to the psi squared divided by 2. And here we get minus b e to the minus psi squared divided by 2. This is looking every time less and less like psi, I'm really sorry. Plus b psi squared e to the minus psi squared divided by 2. Okay, so now let's put this in here. So what this is basically, this is just going to be a times 1 plus psi squared e to the s squared divided s squared psi squared. Okay, I'm gonna try to do it a little better. Psi squared divided by 2 plus b, then we get psi squared minus 1 e to the minus psi squared divided by 2, and this is supposed to be equal to psi squared minus a times psi. But this is supposed to be in the limit, and by the way, psi, as we said, this is just going to be a to the e psi squared divided by 2 plus b e to the minus psi squared divided by 2, right? This is going to be in the limit where psi is very, very large. So looking at this, when psi is very, very large, the dominating term, we'll see that this term right here will be of basically very little significance, and so will be these ones right here. So we will see that this is indeed true, right? We'll have this is going to be equal to this term right here, and this is going to be equal to this term right here. So in the limit where psi is very, very large, this seems to be in fact a solution, so that is very good. Now there is one problem, and it is that here this part is not normalizable. This is going to be part of some wave function, and we want that the wave function goes to 0 as our psi becomes very, very large. So this is not an acceptable solution because it's not going to be normalizable. So although it is a mathematical solution to this asymptotic equation, it is not a physically acceptable one. So for that reason, we are only left with, I'm just going to call b a, I like it better, but e to the minus psi squared divided by 2. Okay, so this is the asymptotic solution that we have found so far. I didn't call it psi at first. I'm not sure what I call it, but I probably shouldn't have called it psi because our wave function is psi, right? But we know that our wave function is going to have this term right here. Okay, but as I said, this term is only the one that dictates the behavior when our function has very large psi. So there's going to be some other thing that dominates when we are not at that limit. So we don't know what that is yet. We are just going to call this is going to be some sort of function h that depends on psi. This might be some polynomial, this might be some trigonometric function, I do not know. But we know that it has to exist, right? Because this is only a solution in the limit where psi is very, very large, because in the other case it's just it's not true. Okay, so this is going to be what we have to work with now. So let us now plug this into our Schrödinger equation. Just to remind you, it's going to be psi double prime is psi squared minus a psi. Okay, that's our Schrödinger equation for this case. So we need to find psi double prime. So psi prime is going to be h prime. I'm going to drop this of psi e to the minus psi squared divided by 2 plus, because of the chain rule, h times minus psi e to the minus psi squared divided by 2. So let us now just put this minus here in front. Okay, so now we have to derive once again. So this is going to be h prime prime times e to the minus psi squared divided by 2 minus h prime. This minus is going to come from the derivative, psi e to the minus psi squared divided by 2. Then we have to derive this. Now there's 3 terms here, please do not forget. So the first one is just going to be minus h bar psi e to the minus psi squared divided by 2. The second one will be minus h bar e to the minus psi squared divided by 2. And the third one will be minus h bar, but it's actually going to be a plus now, psi squared e to the minus psi squared divided by 2. Now we can actually simplify this a little bit. Psi prime prime will be h prime prime minus 2 times h prime, right? These two can go together. Psi, the e will be left at the final part, minus h plus h psi squared. So we can actually factor an h here. Okay, where's my eraser? Here it is. Way too small. So we can now factor an h. So we get plus psi squared minus 1 h. And all of this times e to the minus psi squared divided by 2. Okay, so this is going to be our psi double prime, which we have to now put into the Schrödinger equation. So let me just get rid of this quickly. If you need to see it again, you can just go back in the video. I'll make sure to list the timestamp of everything in the description as usual. Okay, so let's now replace this. So doing that, we get that this is going to be equal to psi squared minus k times our wave function, which is h e to the minus psi squared divided by 2. So now we can see that this term right here will cancel out this right here, right? It's exactly the same. You can just multiply this out and you see that it's the same so you can just subtract this. So let us now also add this to the right, to the left side. Well, actually, obviously on both sides, but let us put it on the left side. So we get h prime prime minus 2 h prime psi. Now here we're going to get plus k minus 1 h, and well, that's it. That's it. And all of this times e to the minus psi squared divided by 2 equals 0. So in order for this differential equation to be correct, because now we are finding this h, just to put this into perspective, we already found that that part that works when you go to infinity, but now we need to see what happens in the other place, which is why we're looking for h. So we got this differential equation for h. In order for it to be true for any value, we need this part to be equal to 0. So that is the differential equation that we will now try to solve. Okay, so this has to be equal to 0. Now, the way to solve this is to use what is called the power series method. I hope you have seen it before. If not, I will explain it a little bit, but I will not go too in depth because I just don't have the time for that. We have to focus on other things. But basically what it says is that we have to look for a solution of the form of some linear combination of powers of, well, not x in this time, in this occasion, it's going to be of psi squared. Okay, so that's what we are going to be going with. And I don't want to use n because it might be confusing. So there's going to be, usually we call it cn and we use this word n, the tag n, but as you will see, for convenience, we will just call it j, right? So from j equal to 1, this a is not supposed to be there, aj. So basically there's some coefficients times our polynomial to the jth power. Okay, that's supposed to be a j. Kind of wrote that squared out of inertia. Okay. Okay, so this is the sort of solution that we are looking for. Now, in order to now put this in there, we need to find h prime and h double prime in this form. This goes from 0. Sorry, h prime will just be, let's derive this term by term. When we derive this term by term, get that there's going to be the sum of what do we have? We got aj, but when we derive this, because aj is just a constant, that's why we don't derive it. It's going to be a j coming down times psi, I don't know why I put a parenthesis actually, psi of j to the minus first power. Okay, so in order for this then to be real, our series will now begin from 1, right? This is just the standard procedure for the power series method. And what we can do here is just use a property of this summation of shifting the index. So basically we just go from j to basically j plus 1. So every j now here has to be j plus 1. So a j plus 1 times j plus 1 times, oh, actually that is not going to be necessary, but it is good that I talk about it because we are going to use it next time. Usually we do this, but there's no need because there's an xi multiplying it. So I'm sorry about the confusion. There's no need to do that yet. We will have to do it for the double prime though. That's why I began doing it there. So now h double prime, this will go from, this is just deriving this term right here. So this will begin at 2 because there's two terms that now will not be counted at the beginning. It's going to be a j times j minus 1 because we derived this psi to the power j minus 2. And now we actually apply that I was talking about. So we go from j to j plus 2. So all of these j's will just be j plus 2 now. So it's going to be j plus 2, j plus 1. And the purpose of that is so that this can be to the power j. Okay? And this is going to start at 0 now. And the difference is because now every every j went up, but you still start from the first place. So in order to, like here, you started with a2, and here we still start with a2. If you didn't do this, you would have started with a4, and you would have missed the first few terms. We didn't want to do that, so that's why we had to change this index. Okay, otherwise it's not legal. So now we put all of this into our differential equation here. So this is going to be summation from j equals 0 to infinity of a j plus 2. I really hope I got enough space for this. J plus 1 psi to the jth power minus twice this thing right here. And this psi that is multiplying, I will just put it together with this right here. So this is going to be j equals 1 to infinity aj j psi to the jth power. Now, the most important thing when doing this power series method is that you need to manipulate the series so that the exponent of your x, or depends on the variable you're using, in this case it's psi, but if it's x or whatever, they all have to be the same, right? That's why here we had to do this whole thing so that we could get this to be xi to the jth power and not the minus 2 power, right? And that's why I didn't do it here, so that when it is multiplied by xi, this becomes just j. Otherwise, it would have become j plus 1. And that would have been annoying. Then we would have had to reverse what we just did. Okay, so plus k minus 1 times h. But h is just sum from j equals 0 to infinity. By the way, it starts at 0. I did not change anything there, so it just starts from 0. This, yeah. Okay, so that's going to be a j psi to the jth power, and this has to be equal to 0. So let us now go to the next page where we can now solve this. So let's put all of this into the same summation, right? Because they all start from j equals 0. So we can put it all into just one sum, and we can factor out this psi to the jth power. So we get a j plus 2 times j plus 1 minus 2aj times j. Then we get plus k minus 1 aj, and this has to be equal to 0. So in order for this to be equal to 0 for any psi, this in here has to be equal to 0. So let us do this. A j plus 2, j plus 2, j plus 1. I'm just copying this part. And now I'm going to put all of the other terms to the right hand side. So we get, and I'm going to factor out the aj. So aj times 2j minus k minus 1. There's a parenthesis missing. Okay, so here I get that a j plus 2, this is equal to aj to j minus k minus 1 divided by j plus 2, j plus 1. Okay, so this is an extremely important result. This is the result of our of this power series solution, because this is now going to allow us to find every single term, every coefficient from this solution, right? We said h is just aj, and now we know what these aj's are. We have what is called a recursive formula for aj. So that is good. However, there is a little problem with this still, because these coefficients are just going to keep getting larger and larger as j increases. And that is not good, because these coefficients are going to be part of our solution, of our wave function, and we can't just have them getting larger and larger, right? We need this. In fact, it's going to be exponentially growing. So we need it to have some end. We can't just have it grow forever. So we need that there has to be some point where, you know, some j, right? Some j maximum, where this thing right here will be 0, because that will just truncate the growth of these coefficients, right? Because remember, this just said that, for example, if j is 0, say that the second is just the first one, which is a0 times, well, just replace j in here. So it's going, if you know 1, you're going to know the one that comes 2 steps later, right? That is what a recursive formula is. So if you know the a0, right, that's going to be the first term of the even ones, because as it's always plus 2 plus 2, if you start with an even term, you will get an even, because 0, then 2, then 4, then 6. And if you start with an odd one, you're always going to get an odd one, because you 1, 3, 5, 7, 9, blah, blah, blah. So, well, we know that there's going to be this upper limit. So this upper limit then has to be equal to 0 for some j. So 2j max minus k minus 1. This has to be equal to 0. That is our condition for this to be normalizable. So from this, actually, we can see something that is very interesting, because what was k? K was just 2e divided by h bar omega. K was just 2e divided by h bar omega. So 2j max is going to be equal to, I'm just going to put it the other side. It's going to be 2e divided by h bar omega, and I'm going to leave the plus 1 here, 1 plus this. So now from here we can find this e. So the energy is going to be equal to h bar omega divided by 2 times 1 plus 2 times this j amount, right? This maximum amount, which we might just call n at this point, right? Since it is not just any j, it is a very special j, so let's call it n. So now when we multiply this, we see that our result is just h bar omega n plus 1/2. And we have now gotten back the result of the allowed energies that we found using the ladder operator. So that is pretty cool. So using this condition, we found this right here. So let us now rewrite this expression. I think it's still on copy and paste, right? If I paste, okay, amazing. So this j is now not just a, this is, in fact, well, we can actually now replace it, right? Because we know that this maximum value will be our n. So we can actually replace, yeah, I kind of regretting pasting this right now. I need more space. So we know that our maximum value n minus k plus 1 has to be 0. So let us actually replace this k now. So 2n, let's see, plus 1 will be k. So in this equation, and now I actually want to put it here. Oh, damn. That happens sometimes. So 2n plus 1 is equal to k, right? So aj plus 2, this will be equal to aj times j minus, and now replace this k for 2n plus 1, and there is a minus 1 right there. So actually these minus 1 and 1 will cancel each other out. So we get, well, this is divided by j plus 1, j plus 2. So now this is just going to be 2 times j. Okay, I already forgot j minus n, right? 2j minus n, yes. It's going to be 2j minus n. Okay, so that is going to be the recursive relationship that we need. And in fact, with this, the problem is actually solved. And you might be like, what? Because it doesn't really feel like it's solved, because this is some weird thing. But the problem is the answers to, the wave functions are sadly not of an easy form. But remember, what was our solution? We said our h is going to be this sum from j equals 0 to infinity of a j times, psi to the jth power. So this is going to be a 0 times j to the psi to the 0th power, which is just 1, plus a 1 psi first power plus a 2 psi to the second power, and so on. So what is a 0? Right? Well, a 0 is just going to be some constant, because remember, this is a differential equation of second order. So there are two constants that are unknown. This is classic from this power series method. These first two ones are usually unknown, and we have to determine them through normalization, in fact. So a0 and a1 are just constant that will have to be given by initial conditions or normalization or whatever. So let us begin by a2, because well, I think I'm kind of getting ahead of myself, but let us see, for example, because remember, this n is going to be this maximum level, right? And the maximum thing allowed here is going to be when this here is 0. So what we actually are going to do is take a look right away, remembering that that psi, our solutions to the wave function, are h times, I almost said h bar, h of psi times e to the minus psi squared divided by 2, right? That's our wave function. That's what we have found. It is not normalized yet, so keep that in mind. So this is going to be proportional actually to this. Okay, so let's go for psi 0. This means n is equal to 0. So in that case, this thing right here, it can have a maximum value, right, of 0. This thing right here, we are going to get 2aj, j minus 1. And since this n is 0 here, we go 0. Now our allowed j, there has to be an end. And since n is 0, n, remember, is the maximum allowed j. So if this has to be 0 at the maximum allowed j, then we need that this j is also 0, right? Because this n is the maximum level, and now we are in the ground state, so n is 0. So j has to be matched in order to have that. So when n is 0, only allowed j is also 0, so that this part right here is 0. So that means that a2 is going to be 0, right? Because a2, it's aj, which is 0 plus 2, so a2 is going to be twice a0 times 0. And it doesn't matter what it is divided by, because it's already 0. And a1, it's going to have to be 0, right? Because the only condition was on the even terms, so there cannot be any odd terms. Otherwise, it would grow infinitely, because we only have this one condition. So j has to be equal to 0. So that means that in our power series, right here, the only non-zero term is going to be a0. So this means that psi 0 is going to be a0, that's our h, right? H is only a0 times e to the minus psi squared divided by m. And when you look at this, this is actually exactly what we found using the other method. This is the ground state, right? Remembering that this is going to be a0, and psi, this is just going to be minus m omega divided by 2h bar x squared. This is what we found using the algebraic method. So this seems a lot more complicated, so please, I'm going to do some more examples, but you have to try them for yourself too, right? Because you have to get the feel of this. We are going to do some more problems finding a lot of these states, but it's important that you get a feeling for that because it's really not that intuitive. So now let us go for psi1. Okay, so let's go for psi1 here. So psi1, this is just going to be, what is it? This is n equals 1. So when we take a look at this, we're going to have that 2aj j minus n. This will have to be 0 for this maximum n. But what is the maximum n? Maximum allowed n is 1. So j minus 1 has to be 0. So the only way this works is with j equals 1. J equals 0, it doesn't work. And as we saw before, now we can't have any even terms, right? Because 0 and 2, there's no condition. So if you take any 0, 2, 4, there's not going to be anything. J1 is the maximum allowed value here. So got n equals 1 means j equals 1. So now the only term present in this h function here will be a 1 times psi, right? Because you have to plug it in and it's already multiplied by this psi to the first power. So our psi1 will be some constant times psi times e to the minus psi squared divided by 2. And this is also what we got using the method that we discussed in the previous videos, right? The algebraic method. But the difference is this gives us a general formula. And that is amazing. This gives us a general formula to find any psi we want. Before, you had to start with the ground state and just apply the raising operator over and over again and over again. And if you wanted to find psi 50, you are going to be doing that all day. But now you could just go ahead and put 50, n equals 50 in here. You see which values of j are allowed, and you're going to get it a lot faster. It's still going to be super annoying, but it's going to be a lot faster. So this recursive formula allows us to find what our h is, and we put that into our psi. And that's how we do it. So let's do one more example with psi2, because that's actually where things change a little. So let's go for n equals 2. In this case, we get this 2aj times j minus 2. And this time, there's not just one value allowed. We can have j equals 0, right? This is still going to be less than our maximum value, but we can also have j equals 2, which will be our maximum allowed value. So now we have two of these possible states. So now let us put that into our psi. Psi2 is then going to be this h, which remember we just go here. So it's going to be a0 plus a2 psi squared e to the minus psi squared divided by 2. And that's actually what we got in a previous video. Obviously, we had the normalization constants back then. We don't have them here, but the form is basically the same. So as you can see, this is how you build these states. If you want to go for psi3, you just say, okay, n is going to be equal to 3. You go ahead and look in here and you say, okay, j can be 1 or 3. And then you take the first term, you take the third, which is just a3 psi cubed, and then you put that together. And as you can see, the states are alternating between even and odd, which is something that we also knew from the previous method. So there is that. And now there is a thing about this h, and that's also the reason why they are called h. These are very special polynomials. They are called the hermite polynomials, right? Yeah, I think there's another y or an I. I think it's an I. Okay, well, whatever. The hermite polynomials. So they are very important. We usually write them as h of n. In this case, it's going to be of psi. And the formula for them is actually not easy, as you see, because it comes from this recursive formula. But in general, they are a very well-known group of polynomials because they are very important. In fact, we'll study more of their properties later. And some of the things that of the properties is that they are orthogonal. That is very important. And they are also a complete set, right? So there's that. And now we want to write some general formula for some state psi n of psi. Now we know that this is just going to be some hermite polynomial here. This is basically just our h, our small h. We change the notation because we recognize, okay, these polynomials, this series is not just anything. These are the so-called hermite polynomials. times our e to the minus psi squared divided by 2 times some normalization constant an. And now here is where books, and I also look at videos and I look everywhere, they just slam the constant. They say, okay, this is a constant, good luck, right? But as I said, I don't think that that's a good method to teach. So I spent a lot of time trying to figure it out, and I finally got it. So this is how you find that constant, because the way to find it is obviously to normalize, right? Let's just say psi n conjugate of psi. Psi goes from minus infinity to infinity times psi n of psi. But remember, this is usually the x. So if we want to write this in terms of psi, we have to use our transformation, right? Because psi is m omega divided by h bar x. So a square root of this. So the psi is going to be m omega divided by h bar square root dx. So dx is going to be h bar m omega d psi. All right, so let's put this in here now, and let's write our function here. So it's going to be from minus infinity to infinity of, we get an squared times these hermite polynomials, which are real, so their conjugate is the same. Hermite polynomials times the hermite polynomial times e to the minus psi squared the psi, and well, there's still this right here lingering around, right? Okay, so, and this is where the problem comes, like, how do you integrate this, right? Because these hermite polynomials depend on n, and it's super complicated. And what do you do there? Now, the thing is, these hermite polynomials are actually very well studied in mathematics, and there is actually an orthogonality relationship. Now, I will not be able to prove this because the proof is actually very, very complicated, but I hope that this does help you at least get some insight, because when you multiply hm of psi, hn of psi times some e to the minus psi squared the psi, then this is going to be just, if I remember correctly, let me double check, it is 2 to the n pi. In factorial, sorry. Let me double check. I think it's this. I will just double check because I want to make sure that I got it correctly. It's going to be, yes, okay, here it is. So it's going to be 2 to the nth power n factorial times the square root of pi and times delta nm, of course, because they are orthogonal. So in our case, they are both hn. So this right here will just be hn. So this delta will just be 1. So this here is what we will write for this integral, right? So instead of the integral now, we can just erase it and replace it by what we found down here. So we know this is going to be an squared times 2 to the nth power n factorial square root of pi times this thing right here. Now, well, we already saw this. So now we can, and this has to be equal to 1. We are normalizing this. So an squared, this is going to be, now we just divide everything to the other side. It's going to be m omega divided by h bar pi to the 1/2 power times 1 divided by 2n n factorial. And now we just take the square root. So when we do that, this 2 goes away. This 1/2 becomes 1/4. And this would have a square root. So that is the normalization constant. So when we now put that into this wave function psi n, let me just go ahead and do it here so I don't have to rewrite it that much. Psi n of psi, this is going to be this normalization constant times the hermite polynomial of n e to the minus psi squared divided by 2. So this is what appears on books such as Griffith's, and that is how you find that normalization constant. So I hope that this helped you in some way. If it did, I would really appreciate it if you just let me know in the comments or like the video or something, because it really takes a lot of effort, and well, I hope you liked it. And if there's any questions, just let me know. We will see you then. I will see you then in the next video.